In this video, we'll talk about differentials and how we can use them to help with linear approximation. What is a differential? So if I have y is f of x, and f is a differentiable function, then we define a new independent variable, dx. And this here is a differential. Using this, we can define a dependent variable that's also a differential, dy, which is defined to be f prime at x times dx. So if you're given a value for x and a value for dx, you could plug into here to get what dy should be. This is a different differential. Basically, these differentials are these dx, dy, df things that we're going to have in this section. The idea of defining them this way is the fact that if these differentials exist, then dy is dx times what? Well, this ratio here is f prime, which is dy over dx. So it's kind of like you're canceling out fractions, but you're not, because this thing in here really isn't a fraction. But the ratio of them is the derivative in the right context. So it looks like a fraction, looks like you're canceling fractions, but you're not, because this derivative here is not actually a fraction. In this same context, we can also just use df being f prime of x dx to get the differential of f instead of the differential of y. Different notation, but the same idea in how you work out these things. How is this useful for linearization and linear approximation? The idea is that we're going to set dx equal to a delta x, or a change in x. What we'll get then, our definition of a differential said that df was equal to f prime at x times dx. But now if I set dx equal to some change in x, or a delta x, this becomes f prime at x times delta x. But this here looks a lot like our linearization. Our linearization had that L of x was f at a plus f prime at a times x minus a. I replace this x by an a, that's fine. And this here is really a delta x. It's a change in x values from a to x. So linear approximation tells us that L of x minus f of a is equal to f prime at a times a delta x. But linear approximation gives that this L is approximately f at x. So f at x minus f at a is approximately f prime at a times delta x. This over here is a change in f. And when we're doing linear approximation, we're trying to get at this change in f, because the change in f lets us get the actual value of f, because I know the value at a nice point. So the idea of linearization with differentials is the idea that I can approximate the change in f by the differential of f. And the differential is defined as f prime at the initial point a dx, which I'm really plugging in f prime at a times delta x. The ability to approximate a change in a function value by f prime times change in x, that's how we get at using differentials to help solve these problems. And the stuff we did with the square root of 35.8 would work in the same way. It's just not as direct, because you have to go through this whole change of f step first. But the idea is the same, it would work that way. What would you get that way? Well, f prime at 36, our test point there was 1/12. So my change in f I could approximate by 1/12 the change in x, which was minus 0.2, because I'm going from 36 to 35.8. This becomes by negative 1 over 60. Break down the change of f. Change of f is then f at 35.8 minus f of 36, which is 6. I add that over, and that gets the same answer that I had before. This just gives a new way, a new technique for viewing linearization using differentials, which could be easier in certain situations and more complicated in others. We'll see the easy situations in the next video.